Okay, so here's week 2 of our gravity notes. All right, so the thing that you need to learn this week is that gravity actually exists between all objects, not just between planets and moons and stars and things. It's between all objects. Some of you guys might be familiar with this episode of Family Guy when Peter was getting trouble for being told that he was too fat and that he had developed a gravitational field. So the thing is, no, Peter's not big enough to actually be able to attract the TV like this, but there is a gravitational force, a force of gravity attracting Peter and the television and the apple and the book and the can. And in fact, there's also a gravitational force between the television and the book, between Peter and Brian, between Brian and the couch. There's a gravitational force between any two objects in the universe that have mass, every single one. So you might be wondering then, if there's gravity between literally all objects in the universe, then why aren't things all just mashed together all the time? Well, the reason is that gravity is actually an extremely weak force. It's actually the weakest force in the universe. It's so weak that just, the gravity between my computer and myself is overcome by the friction of my laptop sitting on my desk. Even just air resistance is enough to overcome gravity in some situations. But if gravity, if has enough mass, if there's enough mass between objects or of two objects, and if they're close enough together, then gravity can actually be really strong and why things sit on the ground and things, we can't just jump off of the planet. So like I said, it's the weakest force in the universe. And when we talk about forces, we've talked a lot about pushes and pulls. We've talked about friction. We've talked about the tension force, gravitational force, air resistance, lots of different types of forces. But when we talk about gravity and the gravitational field, that's one of the 4 fundamental forces of nature. And so there's gravity that exists between all objects that have mass. And you can see it has a really low amount of strength, but it has an infinite range. Gravity extends out in all directions. And then we have electromagnetism. Electromagnetism has a pretty strong strength, and that's like electricity and magnets is what that's referring to. And it also has an infinite range. Then we have another force. We have the nuclear forces down here. There's the weak nuclear force. Basically, that's the force that causes some atoms to decay. You guys know that some types of elements are radioactive, which means that they can break apart. And so this weak nuclear force is what causes something called beta decay, when a neutron will actually break apart from an atom when it's unstable. So that's the reason why some atoms are stable and some atoms are not. It's due to the weak nuclear force. And then the last one is the strong nuclear force. And that is the strongest of all of the forces, but it also has the smallest range. And so, like the strength between protons and neutrons, keeping them pulled together, keeping protons, which should repel each other, actually keeping them inside the nucleus, that's due to the strong nuclear force. Now, we're not going to worry about those other 3. We're just going to focus on the force due to gravity. I'll move myself real quick. So the force due to gravity has an infinite range. What that means is gravity can reach infinitely out into the universe in all directions from an object. Now, as it reaches, as it goes out further and further away from an object, it does get weaker, but it does still stretch infinitely. The way that a good analogy for gravity is if you think about a big blanket. If you were to set, say, a marble on that blanket, you can see that the blanket actually curves a little bit. And then if we set another marble in there, that would also curve the blanket, and then they would be attracted to each other. And so I actually have a video for you guys. This is an example of a physics teacher doing an experiment to demonstrate how this works. So let me show that to you real quickly. We won't watch the whole thing. Oh, sorry about that. Let's back it up. There we go.
The explanation for gravity is that matter bends space. And so you put mass in a place in space, it warps space-time, and objects are not feeling a force of gravity, they're just following the natural curvature. And so this is a sheet of Lycra. Where do you get this? This is my old bike shorts. There's literally a spandex.com. You can get a sheet like this if you buy the sale stuff, so you don't care what it looks like, right? For like $20, maybe less, depending on the sale. And so you put matter and it warps space-time. And so if I have another object, it also warps space-time. They feel that and they're attracted to each other. And so that's Einstein's picture of gravity. Objects warp space-time, feel that curvature, and move.
You can see how it gets stronger as they get closer together.
And if you have more mass,
they start bending space
right there
together. They start working together.
If you have more mass, it's going to bend space-time more. And so if you have objects here, you're going to respond to that, right? And so you put something there, now it's attracted. Now, in reality, that big mass would feel the warping of space-time by the marble too, right? It would move a little bit. We usually ignore that.
It's a really small amount,
negligible. The sun move a little bit, but it's so small you can ignore it. The moon makes the Earth kind of wobble around a point 3/4 of the way from the center of the Earth. We usually don't account for that when we're looking at satellite motion. Well, instead of just letting go of one, what if I give it a sideways push? Now it orbits. Now it's losing energy, which wouldn't happen in the solar system, right? Not noticeably. There's some perturbations from other planets and things, but this one does lose energy and spirals in. If I don't push it as hard, it will do an ellipse for a while anyway. So one of the things I thought I would do with this is when you study the solar system, all the planets are going around the sun the same way. Why is that? Did God decide that he only liked clockwise, or depends on whether he's above or below?
Now this is true. All of our planets do orbit around the sun in the same direction.
It wasn't. Different directions. But there was a preferred direction. The form from had a slight preference one way versus another, and things going the opposite way got eliminated, and when it's all said and done, everything's going the same way. That works 90% of the time.
Kind of crazy. Okay, I'm going to pause that for now. It's easy to find that video if you do want to watch it in full. It's just gravity demonstration. If you look up on YouTube, and you'll probably see this guy pop right up. But we're going to go ahead and move on for now. This is another really good GIF, I think, demonstrating how the gravitational field is always there, but it's kind of the strength is changing as that planet is going around. And ooh, I'm mirrored, so it's really weird to watch myself do that. But yes, just so you can see kind of that gravitational field, the strongest part is in red there, and then the weak, as it gets weaker, it's the more blue piece. But you can see that the field is always there. It's always extending out. It just gets weaker the farther out that you go. So how do we know that all of this is true? How do we know how strong or how weak the gravitational force is when we're talking about these gigantic objects, and then we're talking about gravity of people on Earth? How do we really measure all of that? Well, there was an English scientist. His name's Henry Cavendish, and he lived 1731 to 1810. And he's probably most well known for this particular experiment. He did thousands and thousands of incredible experiments. A lot of the same things that Sir Isaac Newton is known for, he figured out at the same time, but he just didn't publish. Like he came up with calculus as well as Sir Isaac Newton, but he just didn't publish it like Newton did. But one experiment that he's very well known for is this one, which is the Cavendish experiment. That's actually what it's called. And in this experiment, he had this apparatus set up in a room, and he emptied that room out of everything else except for just this apparatus. And he even observed it by looking through a small hole in the wall or hole in the door, or perhaps it was a window. I've heard variations on the story, but he would stand outside the room to observe and see, and then come back and measure the motions of this object. And he would see how much had the objects pulled towards each other. And so what he was looking for was how much are these objects actually attracted to each other based on just their mass and how far apart they are. And so he was actually able to calculate that. And this formula, which this was actually the gravitational formula that Sir Isaac Newton came up with. And then what Cavendish did was he figured out what this universal constant had to be. We've said before, last week, we said that the acceleration due to gravity on Earth is 9.8 meters per second squared, or about 10 meters per second squared. That's how fast things fall towards the Earth. That's a constant on Earth, but it's not constant throughout the whole universe. This number, however, the 6.67 times 10 to the negative 11th, so that means move that decimal place over, or rather move it over this direction. If you move that over 11 times, so it'd be 0.00000000067 or 667, that's basically the multiplier for how small gravity actually is. So for there to be a decent size amount of gravity, the masses involved have to be really big, otherwise the gravity is going to be tiny. So this just shows you that relationship. So the G here, that stands for this constant. Then M1, that stands for one of the two objects. M2 stands for the other object. And it doesn't really matter. Like you could say this is the moon and this is Earth, or this is a person and this is Earth, or this is Earth and this is the sun. It doesn't really matter. They're just whatever two objects we're talking about the force between. And then down here, the D, that stands for the distance that's actually between them. And notice it's the distance from the center of one object to the center of another object. Because if we're just talking about to the surface, that doesn't necessarily account for like the whole size of the object. And when we talk about really, really big objects, their actual, size, volume does start to come into play with how much gravity is going to be attracting them. And so then what this really means, if we take a look at this link, so I'm going to go away from the slideshow for just a minute and take a look at this link. You can see this shows you the force acting on these two objects as we can change their mass. So we can do that. Increase the mass. And what do you guys notice here about the force? This is in newtons. It's a really, really small amount, really tiny, because we're talking about gravity between objects that, yeah, those are relatively big objects relative to like just a human, but they're still not that big when we're talking about gravitational force. Because remember, gravity is really weak. So we can increase that. And then what else do you notice about this number compared with this number? The two different forces as we increase. So we've made that as big as we can get it. And if I start increasing this one too, what do you guys see always is the case between these numbers? Do you guys see that that number always is the same for both of them? Okay. Do you remember Newton's third law? So Newton's third law states that for every action, there's an equal and opposite reaction. And what we really mean there is that forces come in equal and opposite pairs. And that's exactly what's going on here. Make this force as small as it can go. That's the smallest that the simulation will allow. And then we can also increase the force by bringing them closer together. But notice this number still is always staying the same. It doesn't matter if I move the red object or the blue object. Both numbers are going up and they're always the same. And it doesn't matter if I increase the mass of the blue object or the red object, the numbers are still always the same. But the point is that as we increase the masses, that makes the force bigger. And then if we decrease the distance between them, that makes the force bigger. So what that tells us is that as the mass increase, the force also increases. But if we decrease the distance between them, that increases the force. So those are opposite, but mass and the force of gravity are directly proportional. So let me go back to our slides now and restart that. Okay. Okay. So remember that as mass increases, the gravitational force increases. And then as the mass decreases, the gravitational force also decreases. So those are directly proportional. Whereas the distance between them, that is inversely proportional. So when the distance decreased, when it got closer together, that caused the force to increase. But then when the distance increased, when it got stretched further apart, when they got spread further apart, that caused the force to decrease. So decreasing the distance increases the force, and spreading that force out, or spreading the distance out, decreases the force. It's weaker the farther apart they get. Okay, now here's one more example that I would like to share with you guys that shows you gravity and its effect on orbits. So this is a nice one. It shows you, first you can do the model, and I like the model because it's easier to see the objects that are involved. You can also make it slow motion or fast motion, whichever you like. And you can simulate Earth orbiting the sun. And you can also increase the mass of the sun or decrease it. Whoop, return objects. And you can do the same thing with Earth. You can increase the Earth or decrease its mass and see how that affects the motion of Earth. And what I really want you to do when you're analyzing that is there is this checkbox here. So make sure that this checkbox is on. This shows the gravitational force. And I really want you to see how the sizes of those forces compare to each other as you make modifications to the mass of these objects. okay? The other thing that's really helpful here is turning on the path. So you can see the path of the object going around the sun. So make sure that you have that path turned on, because it does make it easier to see what, when you make an adjustment, how is that affecting the motion of that planet or of that object. Whoop. And then just return objects if you need to. Another one is you can turn on the grid if you would like, and so then you can really see measurement wise. I'm just going to leave it alone this time, because I do want you to see that as this planet is going around the sun, as Earth goes around the sun, it's not always the same distance away. So you can see that here it's actually closer to the sun, and then it does get a little bit further out. And that's actually true for the motion of Earth around our sun. That is accurate. And so just like in the demonstration on the big plate of blue lycra, when an object gets closer to that center divot, to the sun, basically, it speeds up a little, and then it slows down, and that kind of woo, woo, that does actually happen. So you can see, if you put this on, you can see that the velocity will actually increase a little bit when it gets closer, but it's pretty hard to see that that's happening. You can maybe see a little bit more if we increase that sun, then you can really see that see the velocity change. So you can see it getting smaller when it's further away, and then really increasing when it does get closer. And then the other thing that you can do is you can actually go over to scale side. And so this one, you can see more to scale what's going on. The time is still sped up, but it does tell you how many Earth days are passing. So you can, when it goes all the way around, that's a full year, 365 days, which is kind of funny. It's almost 360, so it's like it's almost going a degree every day, but it's actually a little bit less than a degree every day. But there you go. But that's fun. You can also watch the moon and a planet, or you can watch Earth and a satellite, or Earth and the moon. And still you can have the gravity forces, velocity forces. You can see their relative masses. You can look at the path of the objects. So all of that stuff is still there, and you can still adjust those masses. So you guys are able to play around with that a little bit. These are also options here. And this is actually one of my favorite simulations. I'm going to actually, well, I guess the velocity is kind of interesting, but I'm going to go ahead and turn velocity off on that now. But I do like to see the moon orbiting around Earth as Earth orbits around the sun. I think that's really cool to watch. So I want you guys to play with this, make some manipulations, and then you do need to answer the list of questions that I've posted on the assignment. And I would prefer that you do that in a video, either on Flipgrid, or you can record your video in some other fashion and you can upload it here to this assignment. Or if you can't get that to work, you can always email it to me. Just communicate with me. But the reason that I'm asking you guys to record a video of yourself answering the questions instead of just typing them is because I don't want you guys just writing out something that you don't really understand, or just copy pasting something. I like to hear you guys talk about it, and I think that I have a better understanding of your understanding of the topic when I can actually see your face and hear you guys respond. So if you guys will please answer those questions in a short video and submit those for your assignment this week. And please let me know if you do have any other questions. Feel free to email me or to come visit me during office hours. Remember, my office hours are going to be Tuesday and Wednesday from 11 to noon this week and every week. All right, good to. Hopefully that was helpful to all of you guys. Enjoyed it, and I hope to hear from you guys very soon. Thank you.